This is day 3 of section 7.3 for volumes, and before we get into the new material, I just want to kind of review volumes obtained by revolutions. So when we revolve around the x-axis, if you notice, we have our disks over here about the x-axis, those are dx problems, and our washer about the x-axis, also dx. About the y-axis, we have our disks here, a solid disk, about the y-axis, a dy problem, and here's our washer about the y-axis, also a dy problem. So I'm just going to kind of rearrange these expressions to kind of generalize what's happening across the board here with these revolutions. So if you notice, I scooched over this expression. I'm going to bring the pi in. And the reason why I'm doing that is because if you look at this right here, this is pi r squared. This is the area of a circle. And so when we revolve a region about an axis, we sweep out that circular cross section. And likewise, if I scooch over the two expressions here and distribute the pi, same thing. I've got that outer ring, that outer circle minus the inner circle. That creates that washer or donut. And then likewise about the y-axis as well. And so what we're really doing in general when we find these volumes is we're really integrating an expression for the area, and then we're taking that expression for the area between a lower and an upper bound. And so that's kind of our general expression for volumes, is we are going to integrate an area function. And that's what these are. These are all pi r squared because the cross-sectional areas are all circles. This generalization helps us, though, to extend the volume process to when cross-sections are not circular anymore. So, and that's what we're going to look at today. We're going to look at what happens when these cross-sections are triangular. Here's a right triangle in the purple, or square, or rectangular. So, and this expression will allow us then to extend the process of calculating volume to those cross sections, as well as circular cross sections, like in the orange here. And so, so we call this volumes by slicing, because what we're doing is instead of revolving about an axis, like here's a cone, and we could revolve that about an axis to get that cone. But we could also slice it parallel to its base, and use that general expression for the area to get that same volume. We definitely need to slice things that look like this, because these are not circular. We can't obtain this shape by revolving. We would have to slice these into squares. And so, so the method of slicing then becomes this. The first thing we want to do is sketch a solid of typical cross-section. I'll get more into that when we go through an example. But then we want to find an area function for that cross-section. And then once we have that area function, we just need to see where we want to stack the slices. So those are our limits, and then we can just integrate and evaluate that. So when we look at something like this, here's a shaded region. It happens to be circular, and I want to stack right triangles on top of it. So not only are they right triangles, but they're isosceles. In other words, this leg and this leg are the same length. So if we take a look at what we get,
this solid, what we're looking at is a base of that's in the shape of a circle. So since the circle isn't a function, what we have to do is we have to enter the top half of the circle as the positive square root, and the bottom half of the circle as the negative square root to get that entire shape. And so we're looking at a radius of 2 centered at 0, 0. So this is x squared plus y squared equals 4. And we're going to do isosceles right triangles for the known cross section. So we're going to build triangles going from the top curve to the bottom curve and then straight up at 90 degrees. And then the hypotenuse is going to come down here in the back. So as we sweep across here, I'll keep the increment at 0.2, so we'll have 5 triangles per unit here. So we'll have a total of 5, 10, 15, 20 triangles across here. So looking at building the solid, we can see that as we sweep across the base of the, that circular base, that these triangles are getting taller and taller. You can see that the bottom leg here and the vertical leg here are at right angles. And that since it's isosceles, this leg across the bottom and this leg vertically upward are the same length. So we'll need that to find the area of this triangular cross section. So we'll talk about this for a little bit here. We're going from the top of the circle to the bottom of the circle. And so we're going across that entire distance to get the length of the base. And if I go to the center of the circle, you can see that that length of that base is the diameter of the circle. And so when we look at the functions here, the diameter of the circle is just 2 times the square root of 4 minus x squared. So if we think about y equals the square root of 4 minus x squared, that really is an indication of the radius. So we're just going to double that, and that doubling that basically gets this distance plus this distance. So if we think about it as we come across here, the positive square root is this distance from the red axis, the x-axis, up to the positive y. The negative square root is the distance below the axis. So if we just double one of those, that will give us the length of that base leg on the triangle. So I'll go ahead and complete the solid here as we come back to the right edge of the circle. So now if we look at this solid and rotate this around, we'll see that as we rotate this to the side, we can see that those right triangles here. So we can see that the back is vertical, but it's curved because it's following the curvature of the circle. And that this side here is the hypotenuse. It is also curved because it's following the curve of the circle. So you can see that those are 2 curved surfaces. The bottom is flat, of course, it's just a circle. And we have a vertical back, that's the leg, and then we have a sloping side here, that's the hypotenuse. So we get a shape that looks like that.
So using the information from that video then, just kind of recapping, the top of this circle is not a function, right? It doesn't pass the vertical line test. So we have to look at the top half separately from the bottom half. And so the top half is the square root of 4 minus x squared. The bottom half is negative square root of 4 minus x squared. And so getting an expression for this length here is going to be, since this is measured from the x-axis out, this is going to be 2 times the square root of 4 minus x squared. So that's one side. Now we can use our geometric formula to get the area of this triangle. So the area of the triangle is half base times height. The base is s, and since it's isosceles, the height is also s. So this is 1/2 s squared. So it's 1/2 this squared. So substituting that in then, it's 1/2 times 2 root 4 minus x squared, all squared. And then simplifying this, we square this, we get 4. Divided by 2 is 2, and then squaring this gets rid of the radical. So we end up with 2 times the quantity 4 minus x squared. So this is our area function. It represents this rectangle as it's swept from -2 to +2. So that's our limits of integration. So we can then, as we build this across this shaded region, we can see that as we stack these right isosceles triangles from -2 to +2, and this is kind of just a quick recap of the video, those right triangles get taller until we hit the center of that shaded region, and then they start to get shorter. So that's how we find that volume, and so we're just going to go ahead and integrate that area function. And so our bounds are -2 to +2. That area function is 2 times 4 minus x squared. I'm going to distribute the 2, and then I'm going to go ahead and integrate this. So the antiderivative of 8 is 8x. Minus 2 times the antiderivative here is x cubed over 3. And we're going to evaluate that from -2 to 2. And I'm going to gloss over the fractions, but plugging in 2 into this expression gives us 32/3. And then minus, plugging in -2 here gives us -32/3. So the volume of this solid of known cross-section, of triangular cross-section, is 64/3. Just a quick comment about volume. This goes back to geometry. This isn't in your notes, but if we have these two cylinders and the cross sections are the same, as long as the cross sections are identical from bottom to top, these two solids will have the same volume. That's Cavalier's theorem, and that goes back to geometry. So I tell students to think of this as being like a slinky, and if you push the center out to make it kind of bend, you're not changing the volume, you're just kind of relocating all those cross sections. So if let's look at this one now. In this shaded region, we have a parabola on the bottom and a line on the top, and we're going to build straight up with squares. So here's a quick video about modeling that in GeoGebra. So there is my my shaded region that I want to build straight up and with squares on. And so that shaded region then is going to have on it the edge of one of the squares. And so we can see that the length of the square just goes from the top to the bottom function. And then we get this this three-dimensional shape that is curved front to back, and it's also curved on the top, and then on the back side where the line is just as a straight vertical surface. And so looking at getting the area function for that cross-sectional shape, that square, we're looking at drawing the cross-section on the shaded region. So the way we draw this cross-section, just kind of give you a little art lesson, I guess, is we want to start off by drawing the bottom. And the bottom is going to go from the top curve, which is the function y equals x plus 1, to the bottom curve, y equals x squared minus 1. And so we start by drawing a line segment from the top to the bottom, and that should be parallel to these grid lines here. So you can either decide to draw right on the grid line and connect those dots, or I kind of drew like at about 1/2, so between it. And then since we're drawing a square here, this length is going to be duplicated vertically, so about that long. So to make these look kind of like the same length, because it has to look like a square. And then I'm going to draw the same length segment on the back side. And if we get those the same length, then we just need to connect the top to make a square. And so that's kind of a 3D rendering of what's happening here. And so we need to get the area function for this. So the length of the edge of this square here, then, we call that S. And so that length we get by subtracting this function minus that function. So that's going to be x plus 1 minus x squared minus 1. And simplifying that, then I get x minus x squared plus 2. So that's one edge. So from that, we need to find the area of the square, and we know a square is, the area is found by just side squared. So when I square this, we're looking at an area function of this. And I'm not going to FOIL that out or anything. I'm just going to put that into my integration. So I know I'm going to stack these squares from here to here, so from -1 to 2. And if we didn't have the grid on here, we could just set the two functions equal to each other um, and solve for those points of intersection. So we're going to go from -1 to 2. Here's the side squared, so that's my area function dx. And we're not going to we're not going to FOIL this out. We're going to f int this, and when you f int this, you get 8.1 for the volume of that known cross section. Let's try the same functions. So we're at the same shaded region, but let's try rectangles height 2 now. So here's a short video on again having the top curve x plus 1, the bottom curve x squared minus 1, and I have a rectangle here of height 2. So here's the rectangle height 2. And notice as we build rectangles across the top, since my height is constant, that we end up building this prism sort of shape with a flat top. And so the height of that is constant at 2. That's what this whole idea is. So that height is not going to fluctuate. You're just going to have something that has a flat top like it has a flat bottom. And if you remember back to geometry, we call those prisms. So here's that prism. And so setting up for the volume of that, this is supposed to be a 2 here, it's a typo. Drawing this cross section, and then again we're going to start off with a line that goes from the top to the bottom that is parallel to these grid lines for the appropriate perspective. And then if we notice along the blue axis, the length of 1 is about this tall. So I'm going to draw a line that's about twice that length. Okay, so there's my there's my height of 2. And then I'm going to duplicate that on the back side and then connect the dots on the top. And so there's my rectangle. I need to get this distance s again for the bottom of my rectangle. So that length is still the same as in the previous example, x plus 1 minus x squared minus 1. Simplified, it's x minus x squared plus 2. The height is 2. So we're going to find the area of this rectangle now by taking height times length, which is 2 times s. And so as we multiply that together, then it's going to be that times 2. And I think I distribute, yeah, here we go. So I distribute the 2. It's going to be 2x minus 2x squared plus 4. So the limits are the same. It's going to go from -1 to 2. And here's my new area function. And this we can integrate by hand. So we've got 2 times an antiderivative of x is x squared over 2 minus 2, and then antiderivative here is x cubed over 3 plus 4x. And as we plug in 2 into this expression, we get, just a little simplifying here, we get 4 minus 16/3 plus 8, and that all adds up to 20/3. And then as we put -1 in here, we get negative 14/6. So this is 40 over 6. So 40 plus 14 is 54 over 6, which is 9. So the volume of this solid created by stacking rectangles of height 2 onto this region is 9. So at this point, we should be wrapping up 7.3 now. So this general essential question of how do integrals explain physical quantities, we can kind of come to a conclusion that integration, since it represents accumulation, volume, we accumulate either circular disks when we revolve or known cross sections if we slice, and we can get the expression for either the disk or the area of the geometric shape, and then we integrate that expression. So you should be able to finish up the last section of 7.3, which is the day 3 homework, the known cross sections. If you'd like to take a Blackboard quiz to test out, you can do that this time as well.